right here. Cash flow diagram goes from year 1 through, here it goes from 0 to 4. We use the letter G to designate a gradient. And we see that the gradient starts in year 2 at the gradient dollar amount. The next year, it's 2 times G. The next year is 3 times G. So, and in year 1, it's 0. So here's a description of a gradient, a definition. Cash flows that increase or decrease by a set dollar amount, and we designate that set dollar amount by G each period. So again, some important things with a proper behaving gradient is year 1, the cash flow will be 0. In year 2, payment G happens. In year 2, G, and then it increases by the amount of G in every succeeding year. This is a linear or arithmetic gradient. All right, so for example, we might want to find P, the present value of a given G amount of a gradient. We'd be given the interest rate, I, and the number of periods, N. So we write this in the engineering functional notation for economics. P equals G times, the amount of the gradient times a factor on the appropriate interest rate table. Find P given G for N periods. All right, so here we have a cash flow diagram of an increasing gradient. How much is the amount of the G, the gradient? What is the amount of G in this example? If you said $40, you would be correct. $40 plus 40 more equals 80 in the next year, plus 40 more equals 120 in the next year. So it's the dollar amount, a set dollar amount of increase each period. Is this a properly behaving gradient? Looking back at our rules here, year 1, cash flow must be 0, and year 2, the gradient starts happening. Is that true in this case? Year 1, cash flow is 0, and the gradient starts in year 2. Okay, good, then that's a well-behaved gradient series. Let's do an example here. We'll find the present value of this gradient when interest rate is 5%. So find P given G of $40 times a factor. Undo that. G of $40 times a factor from the 5% interest table. In the gradient series, gradient present worth, find P given G, right? And then the 4-year line. And the factor is 5.1028. So the amount of the gradient times that one factor from the table equals the present value of that whole stream of cash flows that increase at a set amount each year. All right, I wasn't sure if I believed that, so I wanted to do a little proof. Another way you can solve these is to take each year's cash flow and bring it back to its present value, and then simply add up those present values. And you should come up with the same number. So I did that just as a proof. $40 in year 1, find P given F at 5%, that's in the second year. So line 2. So I did $40 times that factor, got $36.28. Then in the next payment is $80, find P given F for year 3, came up with $69.10. $120 for the final payment, find P given F for the 4th year, and so $120 times that factor from the interest table, and then get $98.72, and then add up all of those present values, and I get $204.10. Let's go back and see what I got. Oh, $204.11 using the find P given G method. So 204.11, 204.10, virtually the same thing, just a little bit of rounding. All right, here's a series of cash flows here. Kind of looks like a gradient. Let's see if it's a well-behaved gradient. So here are 2 questions. Question 1, is year 1 cash flow equal to 0? Year one cash flow, oh, it's not equal to 0, so that's a no. Second question, does our gradient cash flow start in year 2? Our gradient cash flow year 2, oh, nope, it's already started. So no. So this is not a well-behaved gradient, right? We can transform it though into 2 cash flow patterns that are reflected on the interest factor tables. So what this is equal to is if you start in year, the first cash flow here, you see it's $100. If you draw a little line like that, you see that every cash flow in this series has $100 in it, right? There's $100 every single year, 1, 2, 3, 4, and 5. So that is here, that's an annuity. Every single cash flow, 1, 2, 3, 4, and 5, everyone has a $100 annuity. Well, that's a pattern that we recognize. Plus, then in year 2, what happens? We have an additional $25. We had $100 here, plus an additional 25. So we plot that here, year 2, $25. Going back up to our original, year 3, we have $100, plus in year 3, then we have an additional 50. So I've plotted down here, $50 in year 3, and then so on. So this is really the amount of the gradient is $25. In year 2, the gradient is $25. In year 3, it's 50, 2G. In year 4, then it's 3G or $75. And in year 5, it's 4 times G or $100. So let's look at year 5 then. Do we have $100 annuity plus $100? It's gradient series, so that adds up to 200 like we had in the initial problem. Does it work for year 1? Year 1, $100 annuity plus nothing equals $100 annuity, or I'm sorry, $100 cash flow in year 1. So we can take a non-well-behaving, a naughty seemingly gradient, like in this example here, and break it down into 2 portions that are well-behaved, an annuity portion and then a gradient portion that is behaving properly, and just add those 2 together. All right, so here I've got $100, the amount of the annuity, find P given A at some I and some N, plus $25, the amount of the gradient, times a factor from the table, find P given G at I and N. So you can multiply those out and then add them together, and you would get the present value of that initial cash flow stream. Let's look at another example. Oh, first we have a decreasing gradient. So these gradients can be going up or down. Here's a decreasing gradient, starts high and it goes down in value. I have labeled this at year 1, labeled at A1. And then the next year is A1 minus G, because remember, equal dollar amounts decreasing each time. And so the last payment here would be A1 minus 5G. So basically we can summarize this. We can break this decreasing gradient into 2 well-behaved patterns of cash flow. Again, if we draw a little line over here, this one's kind of weird, a decreasing gradient, but just follow the steps. If we had pretended like every single year, 1 through 6, had the initial amount of cash flow like happens in year 1, then we would have a cash flow pattern of an annuity like this. Years 1 through 6, assume it's all A1. And then we can subtract from that a well-behaved gradient. What happens here if we take the annuity in year 1, take the annuity amount minus the cash flow in year 1 here? So annuity amount minus 0. What do we get? The annuity amount. What if we take that same annuity amount here in year 2 minus G? Doesn't that equal right here? Annuity amount minus G in year 2, and so on. So then what we have here is a well-behaved gradient, right? Let's double check. Asking our 2 questions. Is year 1 cash flow equal to 0? Year 1, oh, 0, yes. Question 2. Does the gradient cash flow start in year 2? Year 2, gradient, oh, yes. So that is good. So that is a well-behaved gradient that we can analyze using the factor tables. And we have here, subtract that from an annuity, which is the amount of year one cash flow. And we know how to analyze annuities. So the general form then is to find P of this decreasing gradient would be the amount of the annuity times the factor, find P given A, minus the amount of the gradient times the factor, find P given G. And that's how you could find the present value of a decreasing gradient. Let's do an example. The maintenance on a machine is expected to be $155 at the end of the first year, and is expected to increase $35 each year for the following 7 years. What sum of money should be set aside now? Oh, that's probably going to be P, right? Set aside now to pay the maintenance costs for the entire 8-year period. So we're looking for P, what sum of money to set aside now for this set of cash flows that starts at $155. Sounds like an annuity. And is expected to increase $35 each year. Kind of sounds like a gradient. Let's take a look, assuming 6% interest rate. Go ahead and pause the video and draw a cash flow diagram of what that series would look like. Hopefully you did draw a cash flow diagram that looks like this solution right here. We're looking for P, find P. Year one, the first payment is $155, and then increases by a gradient by $35 each additional year up to year 8. So N equals 8, interest rate is 6%. So that's our cash flow diagram of the problem as it's given. Now to solve it, we break it into 2 parts, right? Here is the amount of the annuity that happens. That $155 is included in every year's cash flow. So we have an annuity of $155. We can find its present value by multiplying that $155 by a factor from the interest table, find P given A, 6%, 8 years. And then we add to it another set of cash flows that is basically, let's change color here to something bright. Another set of cash flows is the gradient series, which I'm going to designate right here by this orange. Now, is that a properly behaving gradient? Right here is year cash flow in year one, 0. Well, yes, it is, because the whole amount is taken up by the annuity. The gradient amount is 0 at this point. And does the G gradient amount start in year 2? Yes. So both of our questions are answered yes. Is this a properly behaving gradient series? So it is. So then we can say the amount of the gradient, $35, times the factor, find P given G, 6% for 8 years. So I found those factors from the appropriate table, multiplied, and get the present value of that entire cash flow stream at $1,656.99. So if I were doing this as an engineer for a company, I would say set aside, I would say $1,700. I'd round up a little bit now to pay maintenance costs of this machine over the full 8-year expected life of the machine. You might even round up to $2,000, but at a minimum, it's $1,657, earning interest at 8% each year, making 155 withdrawals the first year to pay the maintenance, and then 155 plus 35 additional dollars each additional year, going up by $35 each year. You should have set aside $1,700 now. You'll make deposits, withdrawal, so that you should end up with approximately a 0 balance or a small positive balance at the end of the 8 years in that particular account. All right, that is a quick teaching on gradients, increasing and decreasing, and how you take a non-behaving cash flow and turn it into an annuity plus or minus a gradient. Thanks. We'll do some practice problems. The end.